this, perhaps it is easier to look back to see how things were at the beginning. Click the buttons to get more information. Personnel were plentiful in most situations. It was not unusual for one operator to be solely responsible for one machine. The supervision and the control were performed by the human being. As far as fuel oil was concerned, density was low compared to today's standards. The process fluctuation in density, viscosity, temperature and flow did not have such an influence over the interface position in the bowl of the purifier, and there was less risk of losing the water seal. The first kind of automation applied to the separator for marine and power application was the alarm for loss of water seal. This made it possible to operate the purifier without an engineer or operator watching over it. If the oil flowed out of the water outlet, it was detected by some device and some automatic action was taken, like shutting a feed valve or stopping a feed pump. Up until this point, it had still been necessary for the engineer or operator to attend, to manually put the separator through the discharge sequence, and so the sludge collected at the periphery was ejected. There was not an absolute guarantee that the engineer or operator would attend to the separator at the required time to initiate the discharge. It could be during a break. The first kind of electromechanical controller was introduced to ensure that the separator was discharged at the correct intervals. As electronic components reduced in size and increased in reliability, so they could be used in process applications. The microprocessor-based controller, like the EPC 400, was a natural progression of sophistication and reliability. Controls that are part of the conventional separator installation. The opening and closing water which facilitates the discharge. The displacement and conditioning water that is added to the bowl. This was previously called the sealing water in conventional systems. If oil is still going out of the oil outlet, we have not lost the water seal. This is monitored by a combination of high and low pressure switches, or a flow switch in some systems, in the cleaned oil outlet. Valve actuation and motor stop function for fail-safe operation. These functions are activated from the controller. Additional controls that are part of the ALCAP installation. The capacitance transducer. The water drain valve. EPC 400, Electronic Programmable Controller. The number 400 is just a designation, but basically identifies it as a controller for ALCAP-type separators. This is how it looks from the outside. Point and click on the buttons to find out what each item is called. The top button is for starting and stopping the preheater, but sometimes this can be controlled independently of the EPC. To select type of heater, see the parameter list. Click on this button now. Click the button again. Point and click on the buttons to find out what each item is called. The second button from the top is for starting and stopping the separation process. This begins a sequence of events which ends up with oil being supplied to the separator. Click on this button now. This LED will continue flashing green if a PT100 is connected to the EPC and the temperature is below the low alarm point. The process will not start until this situation is rectified. Pressing this button again puts the process into stopping sequence. A sequence of events commences which safely stops the process and the separator. Click. This indicates the stop sequence is running. When the oil is no longer supplied to the separator, the green LED goes out and the yellow LED is continuous. The separator can be restarted when the yellow LED goes out. The timing of this depends on the parameter settings. Point and click on the buttons to find out what each item is called. The third push button is for initiating a manual discharge. Normally, discharges are timed or initiated by an increase in the transducer value. Point and click on the buttons to find out what each item is called. The bottom push button is for alarm acceptance and reset. The LED to the left flashes red when there is an alarm. Click the button once to accept the alarm. Click the button again to reset the alarm. When in normal operation, this bottom button can also be used to make the display indicate some special information. We will now simulate normal operation. You will get an explanation of the different stages and examples of what could be indicated in the display. Click the button now. You can now choose to step through this display. First, select the type of ALCAP separator, FOPX, MFPX or LOPX. Keep this button pressed and a LED test will be performed in a few seconds. Click the button now to see the LED test. Point and click on the buttons to find out what each item is called. The electrical supply for the EPC 400 is 48 volts AC. Click on the door handle to open the door. Alfa Laval calls the versions of the circuit card generations. The yellow stripe along the top edge indicating this is a Generation 2 circuit board. To see the difference, click the buttons. The power on-off switch for the supply to the board. Note: the supply to the outputs is still live. The selection switch for remote, local or programming mode. the push buttons for stepping through the different stages of programming. The information labels are on the inside of the panel door. If we want to look behind, we can just undo the screws like this and carefully lower the circuit board. The part number is located on the top side of the circuit board frame. We will now look at how the EPC 400 works with the capacitance transducer. The EPC 400 supplies an operating voltage to the transducer. This electrical supply is adapted by the oscillator in the housing of the transducer into a format that suits the capacitor's needs. The capacitance value measured by the transducer is proportional to the dielectric constant of the oil flowing in the outlet line from the separator. The EPC uses a measuring circuit to take a capacitance proportional signal from the transducer. The measured value is checked by the EPC 400 against a stored reference and action taken when necessary. What is happening in the Alcap bowl for this to be of any use? In the beginning, there is a little water at the periphery of the bowl. The origin of this water will be explained later. The purpose of this water is to keep the solids, which are separated from the oil, from becoming too sticky. The oil feeds to the bowl. The bowl fills inwards from the periphery. When it reaches the level ring, it flows over into the oil pairing chamber. The oil being picked up by the pairing disc and discharged through the cleaned oil outlet. Some water separates from the oil. As the drain valve is normally closed, the water cannot immediately pass that way. As the water is separated, the interface will move inwards until it reaches the disc stack. When the interface reaches the disc stack, a fraction of water will move inwards and upwards along the underside of the bowl discs towards the outlet. These drops of water then pass with the oil over the level ring and into the oil pairing chamber. The drops of water are then pumped away with the oil by the pairing disc. This changes the overall dielectric constant and will cause a change in capacitance reading. We will now give you a representation of what the transducer feels. Let us consider the transducer having an actual value of 280, with no units attached to it. This is only the way the EPC displays the signals received from the transducer. This value can be seen by stepping through the display with the Alarm Accept button. The EPC now looks at the actual transducer value in detail. What you see here is the trigger range of the EPC. 0 on the trigger range is the stored reference of the transducer value. At 100% is equal to about 0.2% increase in water content of the oil. The trigger range is displayed by 0 to 100% in the left-hand side of the normal display. When the trigger range reaches 100%, the display changes to double dash. The EPC now takes some action to reduce the water coming out with the oil. We now say it has reached the trigger point. Let's now look at how what is happening inside the transducer is indicated in the EPC 400 display. The left-hand side of the display is an indication of the change of the amount of water in the oil. This is called the percentage trigger range. The right-hand side of the display indicates the time to the next timed discharge. Let's now look at how instructions are given to the EPC for different situations. Click the buttons to get more information. If the EPC 400 had been designed to fulfill one purpose in exactly one situation, then all the instructions the processor would have to perform could be fixed from the start when the units are dispatched from the factory. This is not the case, as the EPC 400 has been designed to control a range of ALCAP separators, which end up being installed in a vast array of different situations. For this reason, we need to be able to give the EPC some data which enables it to function correctly in different circumstances. These variables are known as parameters. The process parameters can be adjusted easily and as often as required to meet changes in the operating conditions, such as the time between discharges and the oil temperature alarm points. As the name suggests, these are dependent upon the installation and include such items as the actual type of separator being used and the type of heater, if any. Installation parameters are normally set at commissioning and do not usually need changing. The timer sequence parameters control the operation of the start, the separation and the stop sequences. During the discharge sequence, all solenoids are also controlled. The service parameters enable the EPC to display timer countdown of the sequence parameters and certain historical data used for trouble tracing in case of faults. This can be accessed by Alfa Laval service engineers.